doing another show. No. Our MC for the day is Vikash, and he's the next act. So now I'm going to be the MC. So do you like science? Good. Do you like magic? Yeah, because he does them both. Ladies and gentlemen, please put your hands together for the science and magic presentation by Vikash. Take it away, Vikash. How are you all doing today? Oh, come on. Just good. How are we all doing today? There we go. My name is Vikash. You might have seen me MC out here, just like Eric said. And right now, I'm going to be doing a science show. Are you all interested in seeing a science show? Yeah. Well, I'm going to be doing a science show. But before we get started, I want to say one thing. Science is everywhere. For example, in the air around us. There's hydrogen gas, oxygen gas, nitrogen, helium, all sorts of gases around us. And the cars out there, the wheels and axles, the motor, the gasoline that helps run the car, there's science there too. There's science everywhere and anywhere. Now, I just have a question for everyone. Do you know a late 2017 toy that's really famous? Any toys in 2017 that are famous? Anyone? Fidget spinners, yes. And just in fact, I have brought a fidget spinner along with me. This is a fidget spinner, a modern 2017 toy. I don't know, you just spin it. But this is a really good way to explain science. There's so many science principles in just a simple thing, like a fidget spinner. For example, there's the momentum in the blades being pushed around to cause the fidget spinner to spin. You got the ball bearings in the center. They look like this. There's two metal pieces, and then there's balls in between, allowing the fidget spinner to spin. You got centripetal force, a force that allows these blades on the side to keep rotating around the main source, which is my hand. So there's so many things in just a simple thing like a fidget spinner. Now I just want to show you a quick experiment with a fidget spinner. You can do this at your home. You take a pencil. You can take a pencil like this, and I'll show you the pencil falls down. They won't stay. Now I'm going to take the place where you put your fingers on the fidget spinner off. Just like that, I took it off. And I'm going to poke the pencil through the fidget spinner, like that. With the help of the metal at the bottom, the fidget spinner will stay there. Now I'm just going to spin the fidget spinner, like that. And the pencil should stay. See that? Yeah? Quick experiment, you can do it at your house, friend's house, hotel, apartment, anywhere, even right here on the ground. It's a quick experiment. I know lots of you have fidget spinners. How many raise your hand if you have a fidget spinner. Oh boy, that's a lot. And yeah, this is a quick experiment. It uses centripetal force, like I said earlier. My hand is the main source of the energy causing the pencil to rotate around the fidget spinner. Now, that's just a quick experiment. Can we get started with the science show? Can we get started with the science show? There we go. For a second I thought I lost you guys there. Now, here I have a balloon. I'm going to blow up the balloon. Okay, I've blown up the balloon, and inside I just have some confetti. Now, I also have a wooden skewer over here in my handy-dandy box. Now, what do you think is going to happen when I poke the skewer into the balloon? It's going to pop? Okay, let's see what happens. 3, 2, 1. It pops. Now, we're going to do it again. Now we're going to do the same thing again. Let me blow up this. Now this time, I'm not going to poke the skewer through the sides of the balloon. I'm going to poke it in the area where I just blew the balloon. Up here. What do you think is going to happen when I poke the skewer at the top of the balloon? It's going to pop? What do you think? You think it's not going to pop? Okay. Let's see what happens. Ready? 3, 2, 1. And just like that, I don't know if you can see it. Can you guys see that? The skewer went through the balloon, and the balloon has still not popped. I'll hold it up here. So, see, the balloon has not popped. Now that's pretty cool. Now you're all wondering how that happened. Well, let me tell you. In the sides of the balloon, on the sides, the rubber is more like this. So the tension is really high. So even if you were to pop the balloon right there, you would make a hole in the balloon. The rubber around it would try to cover up that hole, but that also would break open, causing the air to rush out, and that's where you get that big popping noise. But when I do it right here at the ends, right here, that's where the rubber is more thick together, so it looks kind of like this. So even if I were to poke a hole, in the balloon, the rubber would just come around it. That's why the balloon doesn't pop. When I poke the balloon right here on the side, the place where I blow it, then on the sides. Now my next experiment is going to be using some water. Take off the cap. Some water and some ice. I put the ice in a thermos so that the ice can stay cold. Okay. Now I have an ice cube. I'm just going to place it in the water. This is another experiment you can do at your home. In fact, all these experiments you can do at your home. Now I put the ice cube in the water. Can I have a volunteer to come out and help me on stage with this experiment? Someone that's... Okay. Yeah, you want to come up and join me? Yeah. Please give me a round of applause. Now, you know what that is, what I just told you, right? Water. Water is H2O. And you know what the ice cube is? No. It's the same thing. It's H2O. Cube. Get it? Cube? Get it? Okay. It's just a quick joke. Okay. So it's actually, water is just H2O. It's just in a frozen it's in a frozen matter. Now, you see this? This is thread. If I were to give you this piece of thread and ask you, can you take the ice cube out without touching your fingers on the water and the ice cube, and only use this thread, would you be able to? Okay, let's see it. He says yes. Let's see it. Let me move these two poles. You're touching the water. That's okay. He's kind of struggling. Please give him a great round of applause just for trying. Thank you. You can have a seat. Thank you. Now, he couldn't do it because the water has a really high density. That's why the stream couldn't go through it. But I'm going to take another ice cube. Put a couple more ice cubes in there, just to show you. Put a couple ice cubes in there. And I'm going to put the thread around on the ice cubes, just like this. Okay, now I'm going to take some salt. Right here, I'm going to take some salt, just tap it over the thread where the ice cubes are also. Now let's all count to 10. You know how to count to 10, right? Okay, good. You guys all passed kindergarten. Okay, ready? Let's count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's been 10 seconds. Not 10 seconds, but we counted to 10. And just like that, we can take an ice cube out with the thread. Now again, the main question is how did I do that? Well, it's a really simple thing. Let me explain to you. So when I put the thread on top of that ice cube, and I poured some salt onto the ice cube and the thread, that caused the freezing temperature of the ice to drop, causing then the ice cube to melt. Once the ice cube starts melting, the thread starts to sink into the ice cube. And because there's salt on top of the thread, the salt just comes onto that thread. You also have the other ice cubes in the water around the thread, and the salt trying to freeze the ice cube. So it is trying to prevent the ice cube from melting, like I said earlier. So that therefore causes the thread to be stuck in between the salt pieces, and you can therefore take out the ice cube because the thread is stuck to the ice. Now, that's just a quick experiment you can do at your home. Okay, Now my next experiment is going to be using a bowl. Don't mind the string, that's for another experiment. I'm going to be using a bowl and a can and some cloth. Now this is not any ordinary cloth, this is cheesecloth. So I'm going to pour some water into the can with some cheesecloth. There we go. Okay. Now, if I were to ask you, if I were to ask you, what do you think is going to happen when I turn this can upside down? Yeah, what do you think? It's going to fall down? It's going to spill? Is that all we have? Yeah. It's going to stay in. Okay, let's see what happens. Ready? 3, 2, 1. And just like that, like he said, the water stayed. Now, some water did fall out, but most of the water stayed. Now, again, the question is why? Do any of you know why that happened? No? Okay. Well, that's okay. Let me tell you. Water is trying to be pushed down with the help of gravity. At the same time, air is trying to push the water in. So when you have those two equal forces trying to act on each other, the water is not able to come down. So that's why it looks like anti-gravity sort of thing. But when I tilt the can just like this a little bit, see how the water comes out? Over on this side, the water thickness is becoming less, then allowing the air to come in, and then pushing the water out, then causing the water to come out just like that. There we go. Our next experiment is going to be using a bottle and a balloon. It's a pink balloon if you're asking what color. Now I'm going to blow some air into the balloon. I've blown air into the balloon. Now I'm going to show you a cool magic trick. Are you ready to see it? 3, 2, 1. Do you see that? The balloon was deflating. Let me show you again. 3, 2, 1. And just like that, the balloon deflates. Now, I'm not going to be like Eric Michaels and not tell you the secret. I'm going to tell you the secret to this experiment. Well, let me tell you how that happened. So it's all with these 3 holes. Do you guys see those tiny 3 holes at the bottom? Yeah. Those 3 holes are the main key to this experiment. Well, magic trick also. So when I'm blowing air into the balloon, the air in the balloon is pushing the air out of the 3 holes. If those 3 holes weren't there, the air will be just stuck in the bottle, then causing a higher pressure. And pressure moves from high to low. So that therefore causes the air in the balloon to come right back out. So that's why when I made the 3 holes and blew air into the air in the balloon started to push the air out of the bottle and come out of the 3 holes. And I made the balloon stop. Do you guys see that? The balloon just stayed placed when I was about to start the magic trick. That's because I closed the holes. So even if air were to come out of the balloon, there would be a big vacuum in here, then causing everything to be sucked in because there's a vacuum in the bottle. Let me show you again, except this time I'm going to explain how we did it. So right now I just blew up the balloon and I covered up the 3 holes with my finger. When I let go of the holes, see that? The balloon deflates. I'll close the hole up again and the balloon stays in place. It's another quick experiment you can do at your house. Now over here, I got this bucket and a bunch of orange wire and some H2O water. And I'm going to rotate this bucket 360 degrees. At one point, this bucket will be completely upside down. What do you think is going to happen to the water when it's completely upside down? You'll stay in, stay in, fall down, spill. Okay, let's see what happens. Ready? 3, 2, 1. And just like that, the water does not come down from the bucket. Now again, the question is how, why? Yeah, I'm getting to the explanation. It's my show. Okay? I'm getting there. So the water does not come down with a couple principles that let me tell you about. So there's momentum. The water in here wants to keep going. So when I push the bottle that way, the water wants to keep going that way. When I push the water this way, the water wants to go that way. But there's the plastic bowl is causing the water to come back in a different direction. That's the momentum being broken when I do this. Now there's also centripetal force. And centripetal force is the force that is being in this circle. My hand is the main source of this energy, and this bucket is going in a big circle, then causing it not to come down. But if I did this experiment really slowly, which I'm not going to show you, the water would come down because there's a stronger force called gravity. And that gravity would pull the water down. But when I'm doing it really fast, the centripetal force and the momentum is stronger than gravity. That therefore causes the water not to fall down. Awesome. Now, thank you. Yeah, you can hold the pause for later, definitely. Okay, my next experiment is going to be using these tall poles and this box. Inside this box, there are a few magnets. They're not any ordinary type of magnets. They're neodymium magnets, or also better known as rare earth magnets. And they're super strong. Can I have a volunteer to come up on stage and help me with this experiment? Yeah, you want to join me up on stage? Yeah, you want to join me up on stage? Yeah. Now I want you to hold on to this pipe just like that. Okay. For this experiment, I'm going to be using 4 of these neodymium magnets. You can use a various amount of magnets, but I'm just going to be using 4 for this experiment. Now, let's see how long it takes for the magnet to go from top to bottom. Okay? Ready? Let's all count. 3, 2, 1. 1. Oh, here. Can you lift this up a little bit so that we can see when the magnet comes down? Awesome. Let's do that again. 3, 2, 1. The magnet comes down in roughly about 1 second. Thank you so much. Please give him a round of applause. And here I got another pole. Do any of you know what type of pole this is? Some bronze? This is actually a copper pole. A copper pole is a metal. The only difference between these 2 poles is that this is copper and this is plastic. Don't want this to fall. Okay. So I'm going to put this magnet down the copper pole. Let's see how long it takes for the magnet to come from top to bottom. Ready? 3, 2, 1. 1, 2, 3, 4, 5, 6, 7, 8. 8 seconds it takes from it to go from top to bottom. Let me show you again. 1, 2, 3, 4, 5, 6, 7, 8. See, 8 seconds. Now that's pretty cool, but I'm going to tell you why and how that happens. So right here, I got this plastic pipe. This plastic pipe, when I put the magnet down, it will come straight down because there's gravity. Well, when I do it with this copper pipe, when you put this copper pipe is a really good conductor of electricity. I should say that first. When you put this neodymium magnet inside, it has a strong magnetic field. This magnetic field, when put down a copper pipe, will then create an electric current. But not a lot. That's why I held on to it. Not a lot. Just a very small amount. So when I put this neodymium magnet down the copper pipe, it produces an electric current. And that electric current will make a smaller magnetic field, its own magnetic field. So at one point, this will be kind of like a magnet. So when I put this down and put the magnet down, there's a magnetic field, and that's an up resistance on the magnet trying to fall down. But there's also another stronger force called gravity, and that is pulling the magnets down to the bottom of the ground. So with that up force, the magnet comes slower from top to bottom. Let me show you again. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 seconds that time. So yeah, it was coming slower from the magnetic field that the copper pipe is producing on its own. And for my last experiment, I'm going to be using this. Yeah, it's toilet paper. Now, if I were to ask you to blow on this toilet paper and make this toilet paper come upwards, where would you blow? Where would you guys blow? In the bottom? Like this? Yeah, that's the way to blow. But scientifically, there's also another way where you can blow this toilet paper. You can blow this toilet paper through the top. Let me show you. You see that? I'm being able to blow it through the top. Now, I use a principle called Bernoulli's principle. And Bernoulli's principle says faster moving air causes lower pressure. That's all he said. Drain. And that's all he said. But there's more science to it. When there's a lower pressure up here and a higher pressure down here, pressure moves from high to low, causing the toilet paper to come from up to down. That causes the air to come up to down. It causes the air to come from up to down. That causes the toilet paper to rise. Now, that wasn't that amazing, but I want to show you something even cooler. So right here, I got a paint roller. I'm going to slide the toilet paper into the paint roller. Can I have a strong volunteer to help me with this experiment? Yeah, you want to come out and help me? Okay. All I need you to do is just hold the paint roller just like that. Just like that. Don't move a muscle. Got it? Okay, good. I think he gets it. So, I'm going to use this leaf blower. It goes up to speeds up to 130 miles per hour. So, like I was saying before, the faster moving air causes lower pressure. And pressure moves from high to low. So this toilet paper should rise up. But because of its very fast speeds, the paint roller will also start to rotate, causing the toilet paper to come outwards. That's all I'm going to say. The science will do the rest. Are you guys ready? 3, 2, or not, 1. So, and just like that, the toilet paper comes outwards. Upwards. It's getting tangled. Thank you so much. Toilet paper. Well, that's all I have for this time. I hope you guys enjoyed, and thank you all for watching.